This is video 8.2, Physics C, about potential energy. Last video we learned about potential energy and the difference between conservative and non-conservative forces. Today we're going to investigate a bit more into two particular conservative forces, the gravitational force and the spring force, and come up with formulas for the potential energy associated with both of them. Now, gravitational potential energy is going to be given by the general formula for energy, potential energy, which is the negative of the work done by the force. And if we look at gravity, we have, let's say, some object moving from level y1 up to a higher level y2. If we look at the work that gravity does there, since gravity points downward, it's negative, opposite the direction of the displacement. Force is mg, and the displacement is y2 minus y1, or delta y. So the work is negative mg delta y. That means the change in potential energy is mg delta y. So this formula tells you how much energy goes up as you raise something to a particular height. Notice that if you're moving sideways, gravitational energy doesn't change at all. It's only the up and down motion that matters. Or if you want to express it in terms of energy rather than changes in energy, you can use mgy or sometimes mgh. I'll use that as well. But if you're measuring height, this is easy to do. Measuring differences in height is easy. But measuring height, you need to have a reference level, or reference point. That's where we call y equals 0. The good news is you can pick it anywhere you want to be as long as you're consistent. So in the same problem, use the same y equals 0 everywhere. Don't go switching y equals 0 randomly. And you can pick it however it makes the math easy. So that's the formula for gravitational energy. Spring energy, or elastic energy, on the other hand, is a bit more complicated. We're still going to use the expression delta U equals negative W. Now for a spring, it has a certain unstretched length. So we're going to call the position the unstretched or equilibrium position. We'll call that x equals 0. And we'll also say that the energy is 0 at that point as well. Now what we're going to do is we're going to stretch the spring a distance delta x. We know that the force exerted by the spring is negative k delta x, and we want to find how much work we do in moving it out to there. So our delta U is going to be the integral from 0 out to x of negative k x dx, or rather that's the work done, sorry. And so the change in potential energy is the negative of that, so that'll make the negative sign go away. 0 to x of kx dx. K is a constant, it comes out the front of the integral, and the integral of x dx is just 1/2 x squared. And so this gives us our familiar formula, 1/2 kx squared, for the energy associated with a spring. Notice that the energy associated with a spring is always positive. It's 0 when the spring isn't stretched, but when you compress or stretch the spring, you store energy in it. Now that was a very short video, and tomorrow I'm going to check question 2 in chapter 8.